video is for the Unit 10 Week 2 Digital Interactive Notebook, the Thursday-Friday notebook. We're continuing equilibrium, and mid-quarter isn't this week, but I think it might be end of next week. Again, the most useful keyboard shortcut we'll be using today is zooming in or zooming back out to fit. So what are we doing in this notebook? Well, we have 4 slides of review, and then we've got 2 slides we're talking about stressing a system versus shifting a system. We'll get more into that later. And then we'll talk a little bit about Le Chatelier's principle before you all do a pivot lab on Le Chatelier's principle. So do have your notebook open while you are watching this video, because part of this notebook will be to watch other people's YouTube videos and take some notes on them. So you can't do all of the notebook just in this video, because I'm not going to play someone else's video in its entirety within this YouTube video. That doesn't make a lot of sense to me. So here is the review page, reviewing some vocabulary. The RXN is short for reaction, is no longer on here. Hopefully everyone knows that at this point. And we'll go from there. I will give people the first letters. And based on the word bank, you should be able to finish it. Pause the video now and do that on your own. On slide 5, there's an embedded YouTube from Fuse School, which I think does a very good job with some nice animations, better animations than I could make, talking about dynamic equilibrium. So dynamic equilibrium is just the more complete name for the equilibrium we've been talking about. It's not a new sort of equilibrium. This is the equilibrium we've been talking about the entire time has been a dynamic equilibrium because it's constantly still moving. So that's how it connects back to what we've been studying. Some of the ideas it goes over are ideas we have talked about in class. And so in this top box, you can write notes on what does this video explain that we have already learned. And some of the ideas may be new to you that we haven't talked about in class. For example, phase change equilibrium and what exactly that means and how it's similar to chemical reaction equilibrium. So you can write about that here. There's a couple people who have asked, like, hey, no offense, but I didn't get it when you explained it, Abbott. And that's fine. That's part of the reason we're bringing in other voices to explain it, is because maybe my style of explaining doesn't always fit how you learn and think. So it's good to have multiple sources. So if you didn't already understand the stuff, you can write that here. And if the video helps you understand it now, you can write down what new understandings you've come to. If you have any questions after the video, there have been some good questions I've seen people write about equilibrium. Just heads up, the person in this video pronounces iodine a little differently than I have. I think they might be Canadian, but it's fine. So pause the video now, watch this other video out of your notebook, and resume when you're done. All right, so hopefully that video gave you some new understanding or just reaffirmed understanding you already had. Now let's apply that understanding to some of these ideas we've talked about before. We've got one of these reactions is reactant favored, the one on the left here is reactant favored, and the reaction on the right is product favored. So if it's reactant favored, the equilibrium constant over here is less than 1. If it's product favored, the equilibrium constant over here is more than 1. So that's where the equilibrium constant is. They're both at equilibrium, but why is this one considered reactant favored? Hint, hint. And why is this one considered product favored? Hint, hint. And then why are both of these reactions at equilibrium? And if you need a hint on that, see the definition of equilibrium on slide number 4. So pause the video now and try that for yourself. All right, moving on to slide number 7. If K, our equilibrium constant, is equal to 5.51, then the reaction is blank favored because K is, well, more than 1, or less than 1. So K is equal to 5.51, so K is more than 1. Based on the notes from the previous slide, does that mean that it's reactant favored? Or does that mean that it's product favored? Hint, hint. And then if K is equal to 5.51 and Q is equal to 8.19, then the reaction is not at equilibrium because they aren't equal to each other, because the concentration of blank is too high. Well, here we've got 8.19 is bigger than 5.15, so Q is more than K, so we have too many products. The concentration of products is too high. So the reaction will shift, well, towards the, there we go. Pause the video now and finish this slide on your own. Okay, moving on to slide number 8. So here we have an example on the left and then some practice on the right. They're set up in very similar ways. We can see we've got a word bank. Oh, and hey, some of the words are already used. This word bank here is just for the left side. It's just for the example side here on the yellow. So you won't be using that same word bank on the practice slide, for example. Okay, so let's take a look at this picture a little more closely. So we've got a forward reaction and a backward reaction. All right. Oh, we've got reactants and we've got products. And it appears that they're balanced until this hand comes out and pushes stuff towards the reactant side. And then after the hand pushes the stuff towards the reactant side, our forward reaction's growing and it brings it back towards equilibrium. That's cool. So what is happening here? Well, step one, when the forward reaction and backward reaction are equal, the reaction is at equilibrium. So like here, oh, they're equal, it's at equilibrium. And then, after the hand disrupts the system, the reaction is stressed towards the reactant side. Oh, the hand comes in and pushes the balance towards the reactant side, so that's why number 2 says that. Okay, so then we've got 4 more blanks here and 4 words in our word bank. So then, so after the hand disrupts the system, the reaction is stressed towards the reactant side. Then the blank reaction increases. Okay, which reaction is increasing, the forward reaction or the backward reaction after the hand leaves? Okay, it looks like the forward reaction increases like that and shifts the reaction. Well, when the forward reaction is going that way is to the right, and to the right is the products, right down there towards the product side. This shift brings the reaction back to equilibrium, where the forward reaction and backward reaction become blank again. Let's see, we've used the word equilibrium from our word bank. We've used the word reactants right there. Oh, here's the word forward, so we've used the word forward. Here's the word right, so we've used the word right. Here's the word products, so we've used the word products. This shift brings the reaction back to equilibrium, where the forward reaction and backward reaction become equal. Whoops, equal. Whoa, no. There we go. Typing's hard. So yeah, after it comes back to equilibrium, they become equal again. That's nice. Okay, so that is the example here on the left. Now let's take those same ideas and kind of the same ideas and the same sentence structures, but for a different picture. We can see here the hand is coming down and pushing the reactant side on the example on the left, and on the example on the right, the hand comes down and pushes on the product side. So it's a little bit different. It's the same ideas, but a little bit different in what's happening. So when the forward reaction and backward reaction are equal, the reaction is at equilibrium. Oh, hey, that's true for both the left side and the right side. Cool. Oh, that's true for both the example side and the practice side. Cool. So then after the hand disrupts the system, the reaction is stressed towards the, oh, this sentence isn't finished. So on the example side, it said after the hand disrupts the system, should be the word the reaction is stressed towards the reactant side. Oh, it gets pushed down on the reactant side. What's happening on the practice side? Oh, the hand comes down and pushes it towards the product side. Interesting, interesting. Okay, now step 3. In our example, it says, after the hand disrupts the system, the reaction is stressed towards the reactant side. Then the forward reaction increases and shifts the reaction right towards the product side. Well, what happens over here on the practice one? Is the forward reaction increasing? No. Is it increasing towards the product side? Is it increasing it towards the right or the left? Or, well, look at the picture, look at how this sentence was written, and answer this one on your own. Okay, then number 4, after the shift, after the stress happens and the products get more heavy, and then the reaction increases that way to fix it. This shift brings the reaction back to equilibrium, where the forward reaction and backward reaction become equal again. Is that what happens in this picture? So let's use some of the same language, some of the same ideas, maybe changing a couple words around to finish this slide. Pause the video now and finish if you haven't already. Okay, so let's talk about stressing the system. We've already used this word stressing a couple times before on the previous slide, like, oh, stressed towards, stressed towards. Let's talk about what that means. Stressing means to intentionally throw a chemical reaction out of equilibrium, like, these hands are doing. They're intentionally pushing it out of equilibrium. So why would we want to stress a system? Well, when we're making things, the stuff on one side of a reaction is often more useful than the stuff on another side. So, for example, if we look at the synthesis of synthetic polymer, which is a great material for shoes, we can get that in a reversible reaction with these kind of sticky reactants. Where if it was in equilibrium, we'd have this very nice bouncy polymer for our shoes, but we'd also have a lot of stickiness coming from the reactants. And so in a situation like this, we would want to push it towards the side that's better for shoes and push it away from the messy side. That's why we would want to stress a system towards one thing and not the other. Also a very great example for the Haber process in synthesizing ammonia. So how do we do that? Well, in the previous slide, someone's hand comes in and pressures one side and stresses that side to make more of that side. Can we do that? Well, no. And it's not that you're not allowed to. If you can figure out a way, by all means, do it. But our hands are bigger than the molecules. The molecules are way too small. Our hands are too big for us to go in and physically move molecules around. There's a thought experiment called Maxwell's Demon, but even in that situation, we were employing a make-believe demon to do it and not actually doing it ourselves. You can Google Maxwell's Demon if you want to know more about that. So we can do other things to stress the system towards the products or the reactants. That's not, grabbing molecules and moving them one by one. And that will get us to this thing called Le Chatelier's principle. So there's a part 1 video and a part 2 video. You might only need to watch the part 1 video to get some of these ideas for the lab. The part 2 video is good. It's about temperature and heat, but it's a little more complicated. We'll be talking about it next week. So pause the video now, watch these 1 or 2 videos, and then talk about what ideas in the video are new to you. So pause this video now, watch those videos, and talk about what ideas are new to you. So here's how to stress the system if the system's at equilibrium. And that's if we want to make more products or more reactants. There's 3 primary ways we can stress a system at equilibrium: concentration, temperature/heat, and pressure/volume. So let's explore 2 of these in a lab, and let's explore these 2. So if you go to the very last slide, slide 13, there is a link to the lab in Pivot. It's called Intro to Le Chatelier's Principle, and we can see that there are 3 parts to it. Part 1, where we have chromate and dichromate in equilibrium. Part 2, where we have thiocyanoiron 3 complex ion at equilibrium. And part 3, where we have a hexaaqua cobalt 2 complex ion in equilibrium. So, fancy names. Let's click the image, click the link. And I don't know why they are all out of order like this. If you like, so it's come to my attention that on the student view, these labs are all out of order in a goofy sort of way. I don't usually see it in student view, so I didn't know that until really late in the game, that is yesterday. So if you want to sort these better, you see how there's like name, start date, end date, status, score, actions. You can sort these, you can sort the labs by any one of these. So the easiest thing to do might be going to the start date menu and clicking the up arrow to put them in chronological order, or clicking the down arrow to put them in reverse chronological order, where the most recent one should be at the top. So let's hit Intro to the Chatelier's principle. We haven't yet started it, and let's click View. All right, so save to not run out of things. Intro to the Chatelier's principle score. Right now it's 0 out of 16 because we haven't done anything yet. Le Chatelier's principle states that when a system at equilibrium is disturbed by changing the temperature, the pressure, or any concentration, the system shifts in equilibrium composition to counteract this change. Let's see that in action. So part 1, any shifts in the equilibrium of an aqueous chromate in equilibrium with dichromate system can be observed easily because the two ions are different colors. And here we've got, it's just says pivot interactives and then launch embedded content. What this does is it brings up a YouTube video that shows someone
in this short video,
running a reaction. So the reaction isn't actually spinning here. There is a little magnetic stirrer that's in there that's helping stir it so that we can get it mixed more thoroughly. And what we can see, and it's kind of hard to see because it's a white thing in a white background, but if we slow it down, we can see a little dropper come in and squirt in some more liquid. Oh, there's a drop, there's a drop, there's a drop. Oh, a lot of drops coming in. And hey, it changed color. Would you look at that? As the prophecy foretold. JK, it said it earlier. All right, so here is the equation. We've got, 2 of the chromate ion, and that turns the solution yellow, plus 2 hydrogen ions, and then is in equilibrium. There should be arrows on that equal sign, but there's not, with the dichromate ion, which turns the solution orange, plus some, liquid H2O in the form of water. And then there'll be different squirts in to add alkali to remove some of these 2H ions, and they will also add in acid, which adds in more of the H2 ions. But before we get into any of that, let's answer some questions. Write the equation for the equilibrium between the chromate ion and the dichromate ion. Hint, watch the video above. So which one of these options shows us an equation at equilibrium? Hint, hint. Okay. Question 2. When acid is added, which of the following occurs? Well, it's hint, it says see the adding acid part of the video. So let's go up and find the adding acid. This is adding, oh, that says adding alkali. No, let's skip ahead. Oh, here we are. Adding acid. So it says adding acid shifts the equilibrium to the right. Well, let's see what happens when that acid actually gets dropped in. Oh, there's a drop, there's a drop. You can see a couple drops falling in. Oh my goodness, and it's becoming a different color. It's becoming more orange to the right. So we know the reaction's getting pushed to the right and becoming more orange because that's on the product side. And it said acids increase the concentration of H+, and we know that H+ is, we know that H+ right there is on the reactant side. So we can say the addition of a reactant turns the solution, well, did it turn orange or did it turn yellow? I don't remember. Watch the video up there to check. So, which ion causes the color change? Well, were we adding H+ ions? Were we adding OH- ions? Or were we adding SO24? SO42 minus ions. Well, it said in this problem, acids increase the concentration of the H plus ion, so there we, come on, go. Hey, got it. All right. If OH minus was added, what would occur? Hint, a negative ion would bond with a blank ion. Opposites attract. So, is it the first one? Oh, no, that's wrong. Would a negative ion and another negative ion bond? Oh, no, so a minus isn't going to bond with a minus. What would an OH minus ion bond with? Okay, then it asks, what would happen to the system after the addition of OH minus? See at the adding alkali part of the video. Well, let's go back up to the video and find the part that says adding alkali. Did I skip it? Oh no, here it comes. Adding alkali removes H plus ions. This shifts the equilibrium to the left. Okay, so we're removing H plus ions, and it shifts the reaction to the left. So what color will it turn as it shifts to the left? Oh. All right. So which of these answers captures what we just saw? Once you're done answering all 5 questions in the chromate dichromate equilibrium part 1, you can lock answer and continue and move on to part 2, the thiocyanoiron 3 complex ion equilibrium. So the thiocyanoiron 3 complex is a brown-red species, that might be important later, which forms when yellow-brown, why is yellow 2 words? Iron 3 ions, Fe3+, react with the colorless thiocyanosinate ions, SCN-. Let's launch the embedded content. Ah, look, more test tubes. Hey, that stuff is reddish-brown. Interesting. And then there's an equation here at the bottom. This arrow shows it only happening one way, but as we know with reversible reactions, they can go both ways. All right. So write the equilibrium equation of the Fe3 plus iron 3 ions and the SCN minus thiocyanate ions with Fe SCN2 plus thiocyanoiron 3 complex ion. Okay. Oh, hey, there's an equation right there. That looks exactly like this one here, so that's got to be the right one. What? Oh, this is what the video says, but are we supposed to use a one-way arrow to show equilibrium? I don't think so. So let's find the right answer. Question 2. What color is the FeSCN2 plus thiocyanoiron 3 complex ion? What color is that? Hint, look at the equation at the bottom of the video. Well, bottom of the video, hey, there's a little color right there. And also, if we scroll up even further, ding, ding, ding. So there's our answer to that question. Number 3, when 10 drops of iron 3 nitrate are added to the system, what is observed? Hint, see the 1 minute 47 mark of the video. Okay, let's go to the video, play, find, 7 minutes 41 seconds. I don't have time for that. It's a good thing I was told exactly where to go. 1 minute 47 mark of the video, and click. All right. All right, so let's take a look at this test tube on the far right here. Oh, there's some solution that got poured in right there at the 1 minute 47 mark. We can watch it again. And hey, there it goes. So what just happened there? Well, Did the solution turn a lighter shade of red? Did the solution turn a darker red color? Did the solution form a precipitate, or did no change happen? Click your answer and then submit the right answer there. Question number 4. What happens to regain equilibrium after we add 10 drops of iron 3 nitrate to the system? Oh, that's the thing we just did in question 3. So 2 of these answers say that it turned a darker red color. Well, did it turn darker red? Or 2 of these answers say it turned a lighter red color. Did it turn lighter red? Well, what happened in the 1 minute 47 second part of the video? Did this test tube on the far right turn a darker red or a lighter red when we added in that solution? There it goes again. And so that will narrow it down to half of the answers. And then the other half of the answers before this word and, 2 of these answers say the solution shifts towards the reactants, or the solution shifts towards the products, So if we go up here, we can see on the YouTube video on the bottom of the screen that the reactants are the iron 3 and the SCN minus, and the products are FeSCN2+. So if it shifted to become a darker color, that means it's shifted over here towards the products. If it shifted to become a lighter color, that means it's shifted over here towards the reactants. So that will help us answer this question. What happens to the system when 10 drops of 1 molar silver nitrate are added? See the 3 minute 51 second mark of the video. So head back up to the video, find 3 minutes 51 seconds. Hey, there we go. We got our little tube of chemicals there. Hit play. Now we're looking at which test tube? Oh, this one right here. Oh, interesting. Hey, get your hand out of there. We take it out, look at it, shake it around. Ooh, would you look at that? Chemistry. So, question 5, what did we see happen? Well, it looks like no matter what our answer is, a precipitate is formed, and we can tell that because the solution went from pretty clear to pretty cloudy. That's as a precipitate forms. So does the equilibrium shift towards the products and turn darker red? Does it shift toward the products and turn lighter red? Or does it shift towards the reactants and turn darker red? Or shift towards the reactants and turn lighter red? Answer that and go forward from there. And then what happens to the value of the equilibrium constant with all of the above stresses to the system? Concentration of the products increases, so the equilibrium constant increases. Concentrations of the reactants and products change proportionally, so the equilibrium constant does not change. The concentration of the reactants decreases, so the equilibrium constant decreases, or the concentration of the products decreases, so the equilibrium constant decreases. This equilibrium constant, every time it says equilibrium constant, what it's talking about is this K value, the equilibrium constant K. Equilibrium constant K. So that's what it means by that. Do please answer, so it won't let us get on to the hexaquicobalt-2 complex ion equilibrium until we have finished the previous section. So make sure you've answered all the questions before you hit lock and continue. All right, cobalt-2 nitrate dissolves in water, but the cobalt-2 plus ion immediately forms a complex ion with water. Ooh, and we've got this whole thing. This ion is hexaaquicobalt-2, and it's called that, well, hexa, because there's 6 right there. Aqua, well, H2O is water, aqua. So hexaaqua means 6 waters. Here's water, and there is 6 of them. Hooray! And then cobalt-2, well, hey, here's the cobalt, CO, and it's made from the cobalt-2 plus ion, therefore hexaaquicobalt-2. Isn't language fun? When chloride ion is added, a COCl42 minus, or tetrachloro, hey, 4 chlorines is tetrachloro, cobalt-2 ion is formed. Great. So let's launch that embedded content, look at this YouTube video, hit play, and, oh, I see her talking, but I don't hear her. So if I want to be able to hear her, I can click to watch on U10W2.
Start talking about a
And there we
equilibrium.
go. Hey, we have the same periodic table poster in room 285. Fancy that. Oh, good. She's wearing goggles because she's about to do some chemistry. Also, an apron because sometimes chemistry gets on your clothes. In college, once I accidentally, while trying to dispose of a chemical waste section, spilled it all over the front of me, and that was not good. Those clothes were ruined.
Reaction. And this stuff we're using cobalt chloride, and it turns us from pink to blue. And that's how you can tell what the shift is happening with the color.
Ooh, look, there's a balanced reaction there. That might be helpful. All right. Write the equilibrium equation of hexaquicobalt-2 complex ion with tetracobalt-2 complex ion. See the video above. Well, hey, there's part of it, and we can, shift to that part of the video. Shift, like equilibrium, to see our answer. Which one do we think it is? Hint, hint. Which of the following describes what happens? Which of the following describes what happens when a 6 molar hydrochloric acid is added to the system? Hint, see the 1 minute mark. All right, Mr. 1 minute mark, let's see what you have to offer.
I'm adding HCl. So which way do you think it's going to shift?
Right.
All right, let's see if you're right. I'm going to add the acid.
That's right. What did you say?
And it shifted to the right. Okay. I'll put that on that side.
Okay. So we saw HCl adds products to the system and shifts the reaction towards the pink. HCl adds product to the system, shifts towards the blue. HCl adds reactant to the system, reactant, pink, blue. So HCl, Cl. The HCl is where we get our Cl minus from. So is chloride a reactant or a product? If that HCl is where we get our Cl minus from. So if we're adding Cl minus to the system, is Cl minus a reactant or a product? It is a reactant. And then which way did it shift it? Okay. Question 3, what happens to the system when 5 drops of silver nitrate are added? Hint, see the 1 minute 29 mark of the video. So we'll skip ahead. Oh, hey, we're pretty much there already.
Alrighty, so acid made it shift right. Let's try something else now. I have some silver nitrate, AgNO3. I'm going to add some of that. Which way do you think it's going to shift?
Left.
Why? Because? Let's see if you're right. Ooh, what happened?
Shift to the left.
Shifted to the left, but there's something else going on.
Still a little bit darker.
It's like
Pink.
What's different about it?
It's darker.
it's darker.
Stuff on
Cloudy. This is very clear. This has got a little opaque, and there's some stuff on the bottom. You see it? Yeah, there's a little white stuff on the bottom. That's important. You might want to write that down. It's cloudy, turned pink, and it had a pile of white stuff on the bottom.
Okay. So the silver nitrate removes a reactant, forms a precipitate. Well, the cloudiness forms a precipitate. It's going to be part of any one of our answers because it becomes cloudy, and that's precipitate. If something gets cloudy, that is forming a precipitate. Okay, so does silver nitrate remove a reactant, or does silver nitrate add a reactant? And then does it shift? Well, it always turns pink. That's part of our answer. So does it remove a reactant or does it add a reactant? And is it shifting it towards the reactants or is it shifting it towards the products? Shift towards reactants, shift towards products. Well, if it's turning pink, then according to our chart here, if it's pink, it's being shifted towards the reactants. And it's being shifted towards the reactants. Does that mean that it is adding a reactant or removing a reactant if it's shifting it towards that? If it's correcting something. What can be concluded by the ice water bath test? See the 2-minute 21 mark in the video. The ice water bath is the lower one on the left. Okay, let's head on over to 2 minutes 21. Hey, we're pretty much there already.
Okay. Now, one of the other stresses we're going to use is a change in temperature. So I'm going to take this tube and I'm going to put it in the ice water.
It's going to go blue. It's going to go right.
And I'm going to take this tube and put it in the hot water bath up here. Whoa. So the heat has made it turn really, really blue. And if you look at the ice water, it's turned really, really pink. Now your job is to figure out why. Now.
Okay, so we can see the one in the ice water bath. This down here is the ice water bath, where it's in ice water and it's taking a bath. So are we putting in the ice water bath? Does that remove heat? If we put something in ice, does it remove heat, or does putting it in ice add heat? And does it shift the equilibrium right towards the products or left towards the reactants? Well, if it's turning pink, pink is the color of the reactants. So how about that? What can be concluded by the hot water bath test? Well, the hot water bath is the one up here on the hot plate, and that is turning blue. So what do we think? Unlock, answer, and continue. Bing, bang, boom. Please remember to submit for grading. If you don't submit for grading, it will not get graded. So please submit for grading. Also be sure to turn in your notebooks when they're done, because if you don't turn in the notebooks, they're not graded either. If you have any questions, please email your chemistry teacher. Okay, thanks, bye.